Hello, welcome to Chapter 4 of College Physics. In previous chapters we've learned about kinematics, that is, we've learned how to describe objects that are accelerating. We've learned how to track their motion using kinetic description of the motion, and in particular we understand the equations of motion, that is, the kinetic equations of motion that describe objects with constant acceleration. So now that we understand how to describe the kinetics, that is the motion of objects, now we understand how to use the kinetic description of objects in motion, it's time for us to learn about what's causing the motion, and that is forces. And Newton's laws of motion give us the tools to describe the action of forces, how forces act on objects and cause their motion, cause them to accelerate and move around. And really, all the dynamics, that is the motion of objects in the world around us that we can see, we can describe using Newton's laws of motion. So this beautiful behavior here of these dolphins playing around in this cool water. I feel like I'd like to be in that water now, but either way, this and every other kind of motion that we see in the world around us can be described by Newton's laws of motion. And here, Newton came up with these laws of motion back in the day here, published them in 1687, but he developed them years before that, and my understanding is he developed them working all alone, essentially. Newton was a pretty solitary guy. I think it's safe to say he was an epic nerd of his time, the Renaissance time that he lived in, and probably not a lot of people could relate to him, and he couldn't relate to a lot of people. But that doesn't mean he wasn't able to accomplish important things. I mean, he developed these Newton's laws of motion, which we have right here laid out for us. It's quite simple the way they're laid out here, and though they are in fact quite simple, as we see as first, second, and third law, you just look at how simple they look, and they're incredibly powerful. It would be no overstatement to say that Newton's laws of motion truly lie at the heart of science and engineering of our technological world. And do you have to have Newton's laws of motion to have a good life and get things done? Absolutely not. You don't need to understand Newton's laws of motion for a lot of basic stuff. Like, for example, you can build a house, a very good house, even a mansion, castles, and all kinds of great buildings, without understanding Newton's laws of motion in this scientific way, in this very scientifically formulated way. But if you want to build a skyscraper or the Golden Gate Bridge, you better understand Newton's laws of motion, or it's going to be a disaster. If you want to sail across the ocean in a ship, you could probably do that without understanding Newton's laws of motion. If you want to fly to the moon on a ship, now you have to understand Newton's laws of motion. And we could go on like that. So you can see, for technologically advanced society like we have today, we absolutely have to understand Newton's laws of motion. But just to go about everyday life, you don't need to understand them. But for us here in college physics, we definitely want to start learning about and understanding Newton's laws of motion. So let's get ready to unpack them. They're stated here quite simply. First law, body in motion remains in motion, or body at rest remains at rest unless acted on by a force. Second law is F equals ma. And third law, for every action an equal and opposite reaction. They're quite simply stated, but now we need to get into unpacking how these laws allow us to describe dynamics, that is the motion of objects, and statics, that is how they sit still. Sometimes statics could be quite important. For example, if you're building a skyscraper, you definitely want your object to be static, that is not moving. You don't want it to be collapsing and falling onto the next building. So, you want to understand Newton's laws of motion. And Newton's laws of motion are all about force. So what is a force? Well, a force is what gets things going. Simply stated, you could think of a force as a push or a pull, something that gets things moving. Now, forces don't have to get things moving. Only if there's a net force will the something move. For example, here in this case, a tug of war between, we could say, Fred and Bob right here. If Fred is pulling to the left with the exact same force as Bob is pulling to the right, then this crate's not going to move. In other words, there will be zero net force on the crate. because forces are vectors. And they're vectors in 3D. We could use our knowledge of vectors to add the forces in 2 and 3D. But here in 1D, it's quite simple. And for a case like this tug of war, these are forces acting essentially in 1D. There's up and down forces on the crate that are also canceling each other out. The crate's weight is being supported by the floor or the ground here. But we're just assuming that right now, not even worrying about that. The only chance for there to be a net force on this object here, this crate, in this tug of war, is for either Fred or Bob to pull harder. And here it looks like, well, okay, Bob's going to pull harder to the right. What are we going to find out? We're going to find out that crate accelerates. And how could we see that? We could just do it experimentally, in fact. One of the strengths of modern science is that our scientific knowledge rests on experimentation. That is, for something to be considered scientific, a scientific law or a scientific fact, it has to be a natural fact that you can show by experiment. So, for example, if we want to understand the action of forces, really we could just do an experiment. And what's the experiment? It's going to be playing tug of war. So here these guys are playing tug of war, and it looks like they're playing for the prize of a tub of candy in here. That's the prize. Of course, naturally you want to put those candies in your mouth because they're so yummy. So you're going to be pulling for it. And if we said go right here, right, with just one player playing, well, you can guess what will happen if I say go. He begins pulling and accelerating to the left. How do we know he's accelerating? Well, look at the speed. The speed's continually increasing. Okay, and then until he wins the game, and then I don't know why all the candy doesn't dump on him so he can start eating it. But anyhow, so definitely if he's all alone here pulling to the left, okay, then we can see there's a sum of forces all adding to the left. And if you let that go, then he'll begin accelerating. I know he's accelerating because the speed's constantly increasing. Alright, what about if I have another guy who's the same size and strength as the first guy? That is, I have a red guy pulling to the right and a blue guy pulling to the left. And then we say go. Look at the sum of forces at 0. Can you guess what's going to happen? I think you guessed that. Nothing would happen. There's no acceleration because there's no net force. They're both pulling with the same force. And if I add another guy here to the right, red for right, blue for left, he'll start pulling to the right. And now with twice as much force to the right, he'll begin accelerating. And how do I know he's accelerating? Again, the speed is continually increasing. And you probably wouldn't be surprised to find out that the rate the speed is continually increasing is related to the force. In fact, we're going to learn that it's directly proportional to the force. But anyhow, you can see that just for a fact. Put an extra big guy on there, lots of force to the right, he's accelerating to the right. So this gives us our basic concept of forces. Force is what gets things going. And in fact, it's net force. No net force, no go. And it doesn't matter if you put the same force on either side, press go, of course they're not going to go because the forces are knocking each other out. So experimentally, we're concluding, quite accurately in fact, that where there is force, there's acceleration. Right? And here it's net force. It is the sum of forces. If the sum of forces is 0, then there's no acceleration. And if the sum of forces is not 0, then there is acceleration. Now that we understand a little bit better about the concept of force, let's introduce Newton's first law, which states that objects at rest remain at rest, objects in motion remain in motion, unless acted on by a force. That's Newton's first law. And in fact, it was Galileo Galilei that first stated Newton's first law. So perhaps it should be called Galileo's law, but Newton's so smart he gets credit for everything. No, that's not it. But it is called Newton's first law. But let's take a look at how Galileo deduced this law. So Galileo was the scientist that first offered a formal introduction of Newton's first law, or the law of inertia. And this law may not seem like that much of a big deal to us now, but in fact it is a pretty big deal. One piece of evidence for that is that the law of inertia finally supplanted Aristotle's ideas of motion. And Aristotle was a really smart guy, really smart Greek philosopher, and we could even say scientist back in the BC. Aristotle and other Greek philosophers believed that the best way to understand the universe and phenomenon and nature was to think about it logically. And in fact, Aristotle himself is considered the father of logic. And his methods of logical argument lie at the heart today of modern computer science. Aristotle's ideas are quite well thought out, and there's a logic to them, for sure. And that's why it was quite revolutionary for Galileo to come and supplant Aristotle's ideas on inertia. And basically what Aristotle would tell you about inertia, or an object's inertia, Aristotle would say that all objects want to come to a state of rest. So an object's natural state is a state of rest. So an object will remain in motion until it comes to a state of rest. All objects will eventually come to rest because that's their natural state. And it seems pretty self-evident that this is true, because you could take any object around you in the room you're in now, like a bouncy ball or a ping pong ball or any object you want, roll it around, throw it, do whatever to it, and when you come back later, or even pretty soon right after, you're going to find what? That object has come to rest. So clearly that seems like it must be the natural state of objects, is to come to rest. And what for Galileo to come along and say, well, what really is the case is that objects remain in motion unless acted on by a force. That is, they'll just remain in uniform motion. Well, we'll see what we mean by that. And we'll look at how Galileo figured this out. Now, Galileo, he had round balls and smooth track up in his ivory tower somewhere. And here, I don't have round balls and smooth track, but I do have something quite similar, maybe even better. I have Energy Skateboard Park. So we're going to use Energy Skateboard Park FETSIM to conduct the same experiment Galileo did. So what Galileo did was he would start rolling balls, and here we're going to roll our skater from different heights, and he would notice that if I let our skater roll here from a height of 1 meter, let's see what happens to her. She comes back to a height of 1 meter. And in fact, here in her frictionless skate playground, frictionless skating track, she just rolls back and forth between 1 meter and 1 meter. Okay, so that worked. That happened for 1 meter. How about 2 meters? Okay, so what do you think will happen? I let her go. Oh, okay, she comes to a height of 2 meters, so she rolls back and forth between a height of 2 meters. Okay, so, and I could try this. Let's try it. We'll try it with 3. Oh yeah, 3. It's going to happen with any one of these. Let's go up to 5. Won't matter. We can go 6. It'll still work that way. So the skater, just like the balls that Galileo was rolling, his nice smooth balls on his pretty frictionless track, we find rolls until she comes back up to her initial height. So if we start her rolling from the left, she'll roll up to the right until she reaches the same height that she was released from. So how's this giving us the law of inertia? Well, let's see. What if I start to extend my track over here? So this is what Galileo did. He extended his track. Okay, so let's do it now. I'll start her from 1 and let her go. Where do you think she'll go? We've made a long track now. Oh, she goes to 1. All right, so she goes to 1. How about 2? So 2. She goes to 2. So it still works. As long as the track is frictionless, it's still going to work. Doesn't matter how long the track is. Let's think now. Okay, well let's start trying to make it really long. Let her go now. It's still going to work. She rolls all the way up to 1. So how is this telling us that objects at rest remain in rest and objects in motion remain in motion? All right, well, let's think about this case. Let's say now, instead of having the track slope up so that she can roll to her initial height, somewhere where we can see on the screen, let's do this case like this. Let's make it so that we flatten the track. I'm going to make the track as flat as I can. Let's start her from a height of 1. Now we know, okay, so I made the track as flat as I can so that on the right, and here I'm thinking that on the right the track could just go on forever, basically, right? And at some place way to the right, I could think, okay, well, the track goes up again to 1. That's somewhere way to the right. Well, let's let her go here and see what happens. Also watch her speed. Okay, so she rolls down. Now look, she's rolling at constant speed until she just rolls away. Now, we just saw her rolling at constant speed. Okay, we'll do it again. We'll let her go. She's going to come up and reach a constant speed here, 4.3 meters per second, and she rolls at that constant speed, flat away off to the right. When is she going to ever stop again? Well, she's going to stop when that track goes back up to 1 meter. But let's say it never does. Let's just say it just keeps going off to the right like that forever. Then what is she going to do? She's going to roll at a constant speed of 4.3 meters per second off to the right forever. And that is the law of inertia. That is, when she's not being acted on by any forces, and here there's no net forces on her, her force of gravity, which we haven't considered yet, is being balanced by the so-called normal force. That is, the ground will exert an equal and opposite upward force on her. So upwards and downward forces cancel out. And there's no forces on her to the left or to the right. So she's force-free then, just rolling on a smooth track, and she moves at constant velocity. And that is the law of inertia. And this completely contradicts Aristotle's statement that all objects naturally tend to come to rest. We just surmised, correctly so, that the skater will just keep going off to the right forever, as long as the track just goes on forever uniformly level like that and no conditions change. Well, therein lies our deductive reasoning, if you will. We deduce the fact that she'll just keep rolling forever as long as the conditions don't change. Of course, we know in the real world that they're going to change. We could just make the friction lots and grab her back over here and put her there. And something like what we expect will probably happen now. She'll just come rolling to a stop. And so this is what gives rise to the Aristotelian thinking, because in the world around us there's always this thing called friction, bringing things to a stop. And Aristotle never thought to try to set up an experiment like Galileo did, smooth balls on a round track to get rid of friction and see what happened in that case. So therein lies the difference. That's really a big difference between Greek philosophical thinking and modern scientific thought. Greek philosophers thought that you could just deduce everything with logic, just think about things in a very intellectual, pure way. Don't trouble yourself with measurements or messy complications of reality, whereas science is just the opposite. Science says, no, I have to be able to measure and observe phenomena, and what I observe takes precedence. What I observe to happen repeatedly over and over is the fact, and I have to model my reasoning based on that. I have to adjust my models and construct my models so that they match what we can measure and show as experimental fact. Just like we did at Energy Skate Park, where we verified Newton's law of inertia, Newton's first law. Now that we've introduced Newton's first law, let's introduce Newton's second law. This law of motion, which can be verified to be an experimental fact, tells us that the acceleration of an object is directly proportional to the net force acting on that object divided by the object's mass. And the way we define the mass, or the interaction between acceleration, force, and mass, is such that we take the constant of proportionality to be 1. In other words, we take the acceleration to be not only proportional to, but equal to the net force divided by the mass. And this gives us the standard statement of Newton's second law, F equals ma. That is, the net force acting on an object is equal to that object's mass times its acceleration. And here we can see the arrows over the force and the acceleration indicate that these quantities are vectors. That is, they have magnitude and direction. But when we're considering forces in 1D, forces and the subsequent acceleration of an object in 1D, like we're about to do, we can throw away those arrows on top, because vectors in 1D can be represented almost as scalars, because there's only two directions, a positive direction and a negative direction. So vectors that are positive point to the right, and vectors that are negative point to the left. Anyhow, let's go and verify Newton's second law for ourselves experimentally. So here we have an object, this crate here, this 50 kilogram crate, that we're about to put a force onto. And we're going to assume, for the purpose of this experiment, that we have a way to measure these things. So we have some sort of balance scale we can use to measure this weight and verify this 50 kilograms. We have some way to measure forces we're going to put on it, like a standardized spring, where we can measure the strength of the force as proportional to the displacement of the spring, how much the spring gets stretched, something like that. We're just going to take these things to be assumed. And then also we're going to need to measure acceleration. But recall, what does acceleration come down to? Acceleration comes down to kinematics. And that's something that we can measure. Any kinematic quantities like displacement, velocity, acceleration. These are things we can just measure with tape measures and clocks. So now we're going to assume we can measure everything here, all these quantities here. That being said, let's go ahead and see what happens here. So now, right now, what do we got on the object? The sum of forces on it is 0. Well, we're not doing anything to it. And the object's just sitting there. Is that consistent with Newton's first law? Objects at rest remain at rest unless acted on by a force. Well, this thing is just sitting there at rest because it's not being acted on by any force. Okay, well, let's go ahead and put a force on him. Ew, he's still at rest. But notice the sum of forces is still 0. We acted on the object with an applied force of 50 newtons, and then friction went ahead and opposed that force. It opposed the applied force to the right of 50 newtons with a frictional force to the left, also of 50 newtons. And since forces are vectors, the right plus the left adds up to 0. And then we're going to get an acceleration of 0. Let's make sure we understand how to do that. So let's just start off by applying Newton's second law to this situation. So Newton's second law tells us that F equals ma. Force equals mass times acceleration. And both the force and the acceleration are vectors. That is, they have magnitude and direction. And we indicate that they're vectors with these arrows over the top of them. However, the situation we're looking at is 1D. There's only one direction, only one relevant direction involved. The horizontal direction, or the x direction. It's usually horizontal, we're pretty much always going to call the x direction. So in the case of 1D, I can just drop the arrows. Then I'm just going to call it F equals ma. And here, the F really is the net force. When I just write F, I just really mean that that is the net force, the sum of all the forces on the object. Okay, so how am I going to sum all the forces on my object here, get that F? Okay, well, here I can see it's just going to be 50 minus 50, but let's do it a little more carefully. Let's draw a free body diagram. A free body diagram draws a diagram that frees the body. In other words, I'll just think of my body as just this dot. And then onto that dot, I draw all the forces that are acting on the object the dot represents. And here the dot represents that crate. So all the forces on it are two forces, an applied force to the right and a frictional force to the left. So here we have the applied force. I'll call it FA for F applied to the right, and frictional force to the left. I'll just call him little f for friction. So the net force, the F then in this case, is going to be the sum of these two forces. And here now I have to be a little careful, because we can see what the forces are going to add to the net force. They're going to add to 0. We already know that. If I go FA plus the little f, say, and I go 50 plus 50, then the total F net is going to be 100 newtons. And that's wrong. So what have I got to do? I've got to call this the plus direction and this the minus direction. This is the plus x direction and the minus x direction. So we think of the ground, we think of the x-axis being drawn right along the ground, parallel to the ground, and then this is the plus x direction. To the right is the plus x direction, and if to the right is the plus x direction, then to the left is the negative x direction. So really what we have to do here is then go, okay, the net force is equal to the applied force minus the frictional force. And the minus tells us the frictional force is to the left. And then we can see, okay, now we know what those are. That's 50 minus 50 newtons equals 0 newtons. And since that's also equal to ma, okay, well, we know the mass is not 0. We can use our scale to measure it. See, it's 50 kilograms. So since in this case this is 0, well, then that just tells us our acceleration is equal to 0. And since he's just sitting there and not accelerating, he's going to remain stationary right there. So I think it's pretty clear what's going on with that, and how this simple case that we can understand visually with no problems also is consistent with our second law definition. Going back to our simulator, let's add some more force. So we bumped up the applied force to 100 newtons, and the frictional force bumped itself up to 100 newtons. That's the nature of frictional forces. We'll talk a little bit more about those later. But they generally oppose you, and if you can't overcome them, they'll just meet and greet your applied force. Up to some limit, let's see what that limit might be. Well, it looks like we've exceeded that limit now. By going to 150 newtons of applied force, we exceeded the maximum force of static friction. And so the moving friction that this box has on it from the ground, the friction force between the box and the ground, is 94 newtons. So you can see 150 minus 94 is going to give us 56 newtons. And here, I'm going to pause this. That's giving rise to an acceleration, which we're measuring with our tape measures and clocks and stuff that they have for us here, or however they're doing it at this Force and Motion Basics PhET Sim. We can see the measured acceleration is 1.12 meters per second. So let's verify that that should be the case, that that is consistent with Newton's second law. So let's verify that our measured acceleration is consistent with Newton's second law. So in the first situation, the applied force and the frictional force were equal and opposite. They were knocking each other out so that there was zero net force on the object, and we saw quite naturally that produced zero acceleration. The object wasn't moving and it just sat there. Over here, we kept bumping up the force. We bumped it up to 150 newtons, and we saw that the object started accelerating because the frictional force couldn't match that. The frictional force between the box and the ground, for whatever reason, isn't able to go up that high. So now there is a net force on the object. We have the same free body diagram, if we like. Over here, the same free body diagram would apply, except now what's the difference? The difference is that the applied force and the force of friction are no longer equal. Here, this applied force is 150, and the frictional force is 94, so it's 50 minus 94 newtons. And I think I'm going to go ahead and agree with them that the sum of forces, that is the net force, in that case is going to be 56 newtons. Now we know the box is 50 kilograms. So let's say we're given the mass is equal to 50 kilograms. We want to verify that the acceleration should be 1.12 meters per second squared. So what do we have? We have F equals ma. That's Newton's second law. We want to verify the experimentally determined acceleration is consistent with our second law of motion, Newton's second law of motion. Okay, what do we do? Solve for acceleration. Acceleration is going to be equal to force divided by mass. Just divide both sides of this equation, force and mass by mass. Mass will cancel on the right hand side, and we can write acceleration is equal to force over mass. Here in this case, it's the net force on the object. It's 56 newtons divided by 50 kilograms. I'm going to use my calculator now, and sure enough, from here I get that the acceleration is 1.12, and here my units are going to be, okay, well right now, what am I looking at? I'm looking at newtons per kilogram. So all along, I've been calling the unit of force newtons, because in SI units, newtons are the units of force. But let's look at how those units have to be defined. So the units of force, so remember these brackets just mean grab the units, man. What do those units have to be? Well, they have to be the same as the units of mass times units of acceleration. Units of force, by definition, have to be units of mass times units of acceleration. And so therefore, the units of force, which are newtons, have to be equal to kilograms, that's units of mass, times units of acceleration. Well, acceleration in SI units, you may recall, has units of meters per second, or meters per second squared. Meters per second is the same as meters per second squared. And over here then, okay, so I can see what units of newtons are. They're kilograms times meters per second squared, so acceleration has to have units of meters per second squared. The kilogram will cancel out. So our acceleration is 1.12 meters per second squared. Verify that for yourself if you need to. Just substitute kilograms times meters per second squared over here where we have A equals 1.12 newtons per kilogram, just put in what newtons are in terms of their base units right in over here, and then you're going to see that kilograms are going to cancel with kilograms, and all you have left is that, meters per second squared. So here's the units, and we have verified Newton's second law in that case. And we could go on and on like this using the simulation or even real-world objects, because the simulation, of course, is based on real experiments that are done with real-world objects. We're just taking it for granted that the simulation corresponds with what we would actually measure in a real lab, and it does, pretty much, except, well, the simulator is a little cleaner and that it doesn't give us such noisy results. It just gets right down to the business of giving us what the known laws of motion show, what the known and verified laws of motion actually show. So just to wrap up our discussion of Newton's second law, and here considering the case of 1D, all the motion along the x direction, let's go back to our simulator. And let's look at what happens when he exceeds the speed limit here. That's as fast as he can go. So he gives up right here, and then the box starts slowing down. Let's do one more case. Let's turn the friction off. Let's go to no friction at all, and then have him apply a force. Let's have him apply a force of 50 newtons. So now the net force on the object is 50 newtons. The object's mass is 50 kilograms, so naturally the acceleration is 50 divided by 50, 1 meter per second. He's speeding up and up, and once he reaches the speed limit, the fastest speed that this wooden man can push the crate, the wooden man's going to give up, and then we're going to see what happens. The sum of forces on the object is 0. Now there's no force on the object, but what's the state of motion of the object with no forces on it now? It's moving at constant velocity, 40 meters per second to the right, constant velocity, and it never is going to stop doing that. It has no intentions of ever stopping. So it's in a force-free situation, there's no force acting on it, and it's moving at constant velocity to the right. And that is Newton's first law. Objects in motion remain in motion, in uniform constant velocity motion, that is, unless acted on by a force. And one possible velocity that the object could be moving at while no forces are acting on it is 0. 0 is a constant velocity that an object can move at. And that means if it's moving at 0 velocity, well, that means it's just sitting there. And actually, if you happen to be on top of this box, for example, you're just resting on top of that box like that, and if you can't look out and see the world around you, you're just moving on this box that's traveling at constant velocity. Let's say you put another box around the person who's on the box. For all practical purposes, the experience of that person inside the box, if she shuts her eyes, her experience at moving at constant velocity is the same as if she wasn't moving at all. She only knows she's moving if she looks out at the world and see the world's going by her, or if a force acts on this box and she starts sliding around. So it starts to give us an insight into some very interesting properties of matter that might seem obvious when we're looking at them like this, but are not at all obvious if you're not ready to do experiments and build frictionless environments where you can see what happens when you get rid of all the friction, and then we can start to see what the natural tendency of mass is. And mass has this natural tendency to just keep moving in a straight line at constant velocity. That's called the inertial property of mass. So Newton's first law is a statement of the inertial property of mass. With all that said, we can summarize our discussion of Newton's first law, the law of inertia, by noting that Newton's first law is contained within Newton's second law. So of course, Newton's laws all have to be consistent with each other. They all work together like a well-oiled machine to give us a complete description of the dynamical motion of objects. So perhaps it should come as no surprise that Newton's first law is effectively embedded within Newton's second law of motion. So here's Newton's second law of motion, F equals ma. Now in the case when F is 0, the net force on an object is 0, that naturally implies that the acceleration has to be 0, because the mass is not going to be 0. Any object has mass, and that mass is not going to be 0 just because the force is 0. So the acceleration has to be 0. Now let's just consider 1D. Like we were doing, we can consider 2D and 3D, but 1D is just fine. So just considering 1D, meaning that, for example, all the forces just act along the x direction in 1D, then the acceleration is in 1D, and we can drop the overbar arrows. We can drop the arrow over the symbol. So the definition of acceleration is that it's the time rate of change of the velocity, delta v over delta t. And remember, if we start the clock at t0 equals 0, that is, we start our stopwatch, we start timing the action when we click on our stopwatch, so the initial time when the action starts is naturally 0, then the delta t is t. T minus t0 is just t. T is delta t. That's what we've done here. So replace delta t with t. And then the delta v, that's v final minus v initial. Delta is final minus initial. All that has to add up to 0. A is equal to 0 because F is equal to 0. A is equal to 0. And since t is the final time is not infinity, the only choice then for the velocities is that they be equal to each other. That means the final velocity is equal to the initial velocity, which means that velocity doesn't change. So that's just another way of verifying that when no force acts on an object, it moves at constant velocity. Thus an object in motion remains in motion at uniform velocity. Its velocity won't change unless a force acts on it, because unless a force acts on it, its acceleration is 0, and when its acceleration is 0, it moves at constant velocity. So the next thing we'll want to look at is Newton's third law. But perhaps first, before we do that, we should take a look at the difference between weight and mass. That is, now that we understand Newton's second law, F equals ma, how does that make a distinction for us between weight and mass? That should be coming up next.